Hello everyone, welcome to the lecture. In the last lecture, we have started discussing vibrational spectroscopy. We saw that if K is the force constant of the bond, so we can write K. So, this is the force constant of the bond. The potential energy, which is represented by V, can be written as half K x s squared. So, here x equals r minus r equilibrium. So, r is the bond length at any point of time during the vibration, and r equilibrium is the equilibrium bond length. The potential energy can be approximated by a parabola. The steeper the walls of the parabola, that is, the stronger is the bond, the greater is the value of the force constant, as we see from the figure. So, the steeper is the wall, the value of K is large, and if the walls are not that steep, then the value of K is small. So, in order to understand the connection between the shape of the molecular potential and the value of K, we can expand the potential energy, which is a function of r. So, we can expand V of r around the minimum by using something called a Taylor series. So, we have to expand using Taylor series. So, in other words, as the minimum of the potential energy is found at the equilibrium bond length, we will be expanding this V of r around r equilibrium. So, Taylor series is a series expansion of a function about a point. So, the expansion of a function, let us say f of x at x equals a, is given by f of x equals f of a plus 1 by 1 factorial df dx at x equals a times x minus a plus 1 by 2 factorial d 2 f dx 2 at x equals a times x minus a whole squared plus 1 by 3 factorial d 3 f dx 3 at x equals a times x minus a cubed, and we can write also the higher terms 4, 5, 6 etcetera. So, we can expand V of r by writing V r equals V at r equilibrium plus 1 by 1 factorial dV dr at r equilibrium r minus r equilibrium plus 1 by 2 factorial d 2 V dr 2 at r equilibrium times r minus r equilibrium squared plus 1 by 3 factorial d 3 V dr 3 at r equilibrium times r minus r equilibrium cubed plus dot dot dot. So, we can further write this expression because we know that n factorial is 1 times 2 times dot 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 times n. So, 2 factorial is 1 times 2 equals 2 and 3 factorial is 1 times 2 times 3 equals 6. So, we can further write this as V r equilibrium plus dV dr at r equilibrium r minus r equilibrium plus half d2V dr2 at r equilibrium r minus r equilibrium squared plus 1 by 6 d3V dr3 r equilibrium r minus r equilibrium cubed plus dot dot dot. The first term is a constant, which is the electronic energy at the equilibrium geometry or equilibrium bond length. So, this term can be arbitrarily set to 0. In fact, in spectroscopy, we are more interested in the difference between energy levels than the actual energy of the levels. The second term is 0 as the first derivative at r equilibrium is 0. This is because the V of r or the potential is minimum at r equilibrium, and we know that the first derivative at the minimum is always 0. So, the first surviving non-zero term is the third term. This term, as we can see, is proportional to the square of the displacement from the equilibrium position. For small displacements from the equilibrium bond length, r minus r equilibrium is small, and the higher terms like the term I have written here and all the other higher terms can be ignored. As we have already discussed in the last lecture, for small displacements, the harmonic approximation holds good. For larger displacements from the equilibrium position, we have to consider the higher terms. So, we can write this V of r equals half d2V dr2 at r equilibrium times r minus r equilibrium whole squared. So, if we compare this equation with the equation we have already written, that is V equals half k x squared, where x equals r minus r equilibrium, we can identify that k equals d2V dr2 at r equilibrium. In other words, if the potential energy is sharply curved at the minimum or close to the minimum, then k will be large. On the other hand, if the potential energy is wide and shallow, like it is shown here for this curve, around the minimum, that is close to the minimum, then the k is small. So, if we can calculate the potential energy of any particular bond length, then we could determine the curvature, or we can determine what the curvature would be and therefore calculate the force constant k, and thus we can calculate the vibrational frequency. So, now we have to focus on the energy levels of the simple harmonic oscillator. As we have discussed during rotational spectroscopy, one can obtain the energy by solving the Schrodinger equation. So, we can write the Schrodinger equation as H psi equals E psi. The Hamiltonian, that is the H, is given by the kinetic energy operator plus the potential energy operator. We already know that the potential energy is half k x squared, where x equals r minus r equilibrium. The kinetic energy operator depends primarily on the coordinate system being used. So, we can write this kinetic energy operator as minus h cross squared by 2 mu d 2 psi d x 2. So, the solution of Schrodinger equation gives the energy, we can write E v. So, E v equals v plus half h nu. Here we are using or introducing a new quantum number v. So, here v is the vibrational quantum number and nu is the vibrational frequency. So, nu is given by 1 by 2 pi root over k by mu, where k is the force constant of the bond and mu is the reduced mass of this diatomic simple harmonic oscillator. The vibrational quantum number can take integral values like v can be 0, 1, 2, 3, 4. In other words, for every value of v, there is a corresponding wave function and a corresponding energy level. The vibrational energy, that is E v that we have written here, is in joules. So, if we want to express this vibrational energy in the unit of wave numbers, we can write nu bar v, that is given by, as we already know, E v by h c. So, that is v plus half nu bar. As we can see, the vibrational energy depends on the reduced mass of the molecule, because it has dependency on the frequency. The dependence of the vibrational frequency on reduced mass is physically reasonable. Let us say we have two atoms connected by a spring, we have atom 1 and atom 2, and let us say the atom 1 is actually very heavy. Then we can assume that the vibration will be of the lighter atom, that is atom 2, relative to that of the heavier atom. So, if we look into the reduced mass expression, we can write, so we have m 1 and m 2, these are the two masses, and if we have m 1 greater than m 2, so we know the reduced mass mu is given by m 1 m 2 divided by m 1 plus m 2. However, because m 1 is much greater than m 2, we can write m 1 plus m 2 is approximately m 1. So, what we get is M1 M2 divided by M1. So, M1 cancels, we get M2. So, the reduced mass will be approximately M2. Now, if you have a homonuclear molecule where the two masses are the same, that is M1 equals M2, then the reduced mass becomes, so let us say this equals M. So, reduced mass is M1 M2 divided by M1 plus M2. So, it will be M squared by 2 M equals M by 2. But for a heteronuclear molecule, let us say we have a molecule like HI, where the atomic weight of iodine is much larger than hydrogen. So, the mass of iodine is much heavier. In that case, we can write Mi is much greater than Mh. So, in this case, the mu or the reduced mass will be approximately equal to M of H. So, now let us try to draw the vibrational levels. So, we know the energy expression is given by V plus half h nu. So, let us draw the energy levels. So, let us say V equals 0, V equals 1, V equals 2, V equals 3, V equals 4. So, the energies of V equals 0 is, we have to put 0 in this expression. So, what we get is half h nu, that is in joules. If you had put in wave numbers, we would get nu bar by 2. So, for V equals 1, we get 3 by 2 h nu. For V equals 2, we get 5 by 2 h nu. Then we have 7 by 2 h nu. For V equals 3, and we have 9 by 2 h nu for V equals 4. So, the first observation we make is that the energy levels are equally spaced. So, the equal spacing between the energy levels is given by h nu, or in wave numbers is given by nu bar. This observation is different from what we saw in rotational spectroscopy. So, I want to mention it again that the spacing between the energy levels is given by h nu or nu bar. Another interesting point to note is that when the molecule is in the lowest vibrational energy state, that is, when the molecule is at V equals 0, then the energy is half h nu. This energy is known as the 0 point energy. So, for rotational spectroscopy, the lowest energy is 0, but in vibrational spectroscopy, the lowest energy is half h nu, that is, the lowest energy is not 0 even if the molecule is in its lowest energy state. The physical significance of it is that even at the lowest vibrational level, the atom will still vibrate with the energy half nu bar. In other words, the molecule is never at rest. The prediction of the 0 point energy is the basic difference between classical and quantum approaches to molecular vibration. Classical mechanics could find no objection to a molecule possessing no vibrational energy, but quantum mechanics says that the molecule should always vibrate to some extent. So, in order to obtain a vibrational spectrum, because that is the reason we are discussing vibrational spectroscopy. So, because we need to obtain a spectrum. So, in order to obtain the spectrum, transitions should happen from one vibrational energy level to another. We have to ask the question, between which levels can the transition take place? In other words, the question is what change in vibrational quantum number is allowed for a vibrational spectrum, or in other words, what is the allowed value for delta V. So, in the next lecture, we will discuss the selection rules for vibrational transitions. And in the remaining part of this lecture, we will solve few questions on the topic that we have discussed today. So, the first question we have is, consider a homonuclear diatomic molecule X 2. The force constant of the X 2 or the XX bond is K. The atomic weight of X is given as A. So, what we have to do is to show that the 0 point energy E 0 can be written as, this expression has been given. So, we have to show that the 0 point energy can be written as this expression, and in this expression N A is the Avogadro's number. So, we know that the 0 point energy, let us write it by E 0, is given by half h nu. So, we can write this as half h, and nu we can write 1 by 2 pi root over k by mu. So, this is h by 2 pi becomes h cross. So, h cross by 2 root over k by mu. So, we have to find the reduced mass of X 2. So, the atomic weight is A. So, we can write that the mass of one atom is given by A by Avogadro number. So, the reduced mass is A by N A times A by N A divided by 2 times A by N A. So, that will be A by 2 times N A. So, now we can see E 0 is, we have h cross by 2 root over k, and we will put the expression of the reduced mass, that is A times 2 times N A. So, we can write this as h cross root over 2 k N A divided by 4 A. So, this becomes h cross root over k N A divided by 2 A. So, the 0 point energy is given by this expression, and this is the same expression that we have been asked to show in the question. So, let us go to the second question. So, we have two molecules, one is a heteronuclear diatomic molecule, that is A B, and the other is a homonuclear diatomic molecule, that is B 2, and these two molecules have same force constants and are vibrating in simple harmonic motion. The atomic weight of A is 3 times the atomic weight of B, and the ratio of the 0 point energies. So, we have to find the ratio of the 0 point energies of A B and B 2, that is, we have to find E 0 A B divided by E 0 B B or B 2, and this is a multiple choice questions. So, we have to solve the question and see which answer is correct. So, let us find the reduced mass of BB or B2, that we can write MB times MB divided by MB plus MB. So, that is given by MB by 2. So, in the question it is given that the MA is 3 times of MB. So, MA equals 3 MB. So, we can write mu of AB equals 3 MB times MB divided by 3 MB plus MB. So, this becomes 3 MB squared by 4 MB. So, that is 3 by 4 MB. So, we know that the 0 point energy is given by or inversely proportional to 1 by root over mu, and the force constant K is the same for A B and B 2. So, we can write E 0 A B divided by E 0 B B. We can write this as root over mu B B divided by mu A B. So, that will be M B by 2, that is mu A B divided by 3 M B by 4, that is for mu A B. So, this is equals M B cancels. So, we have root over 2 by 3. So, now if you look into the choices, the right answer is choice D. So, the ratio is root over 2 by 3. So, we have another problem. The problem states that the far infrared spectrum of potassium chloride has an intense line at 278 wave numbers. Calculate the force constant. So, we have to calculate the force constant and the period of vibration for KCl. So, we have to calculate the force constant and the period of vibration. The atomic weights of K and Cl are given. So, let us first try to find the force constant. So, let us evaluate the reduced mass of KCl. So, this is given by 38.964 times 34.969 divided by 38.964 plus 34.969. So, this is equal to 18.429 AMU. So, because 1 AMU equals 1.661 times 10 to the power minus 27 kgs. So, we can write this as 18.429 times 1.661 times 10 to the power minus 27 kg. So, we know nu bar is given by 1 by 2 pi c root over k by mu, or in other words, because we have to find the force constant, that is k, we can write k equals 2 pi c nu bar whole squared times mu. Now, if we put in the values, we have 2 times 3.14, then c is 3 times 10 to the power 10 centimeter per second, and nu bar here is given in the question, that is 278 wave numbers. So, we have 278 wave numbers. So, we have to take the square of this entire thing times mu, and mu is 18.429 times 1.661 times 10 to the power minus 27 kg. So, if we do this math, what we get is 83.97 Newton meter inverse. So, we are also need to find the period of vibration. So, we can write period of vibration, this equals 1 by nu, and because h nu equals h c nu bar. So, we know nu equals c nu bar. So, 1 by nu I can write as 1 by c nu bar. So, that is 1 by 3 times 10 to the power 10 centimeter per second times 278 centimeter inverse. So, what we get, the final answer for the period of vibration is 1.20 times 10 to the power minus 13 second. So, the next question we have is the force constant. So, now the K is given. So, the force constant of bromine is 240 Newton meter inverse. So, we have to calculate the fundamental vibrational frequency and the 0 point energy of bromine. The atomic weight of bromine has been given in the question. So, we will start by calculating the reduced mass of bromine. So, reduced mass of bromine is 78.92 times 78.92 divided by 2 times 78.92, that is 39.46 AMU. But here you say this bromine is a homonuclear diatomic molecule. So, the reduced mass, as I said, is given by m by 2. So, we can also get this number 39.46 if we just divide 78.92 divided by 2, this is also 39.46. So, we have to convert into kg. So, we will write 39 times 46 times 1.661 times 10 to the power minus 27 kg. So, we have to find the frequency. So, frequency is given by 1 by 2 pi root over k by mu. So, we can write this as 1 by 2 pi times k is 240 Newton meter inverse divided by mu, that is 39.46 times 1.661 times 10 to the power minus 27 kg. So, whole to the power half, and if you do this calculation, what you get is 9.63 times 10 to the power 12 second inverse. So, the frequency in wave number is given by nu by c, or nu bar equals nu by c. So, we can write this as 9.63 times 10 to the power 12 divided by 3 times 10 to the power 10. So, that will be 321 wave numbers. So, we have found the vibrational frequency both in second inverse and in wave numbers, and now we have to find the 0 point energy. So, the 0 point energy, that is E 0, is given by half h nu. So, we can write this as 6.626 times 10 to the power minus 34, that is the value of H, then 9.63 times 10 to the power 12 divided by 2. So, if we do this, what the answer we get is 3.19 times 10 to the power minus 21 joules.